Welcome! Today we're going to tackle a really powerful way to find patterns in super complex data. It's a method that's, elegant, versatile, and really at the heart of a lot of modern machine learning. Okay, let's dive right in.
So, you know how a lot of methods try to classify data by just drawing a line between the groups? Well, what happens when your data is messy and a simple straight line just isn't going to cut it? Imagine your data points for one class form a circle and the other class is all around it. There's just no way a single straight line can neatly separate those two.
Well, the solution is pretty clever. We just change our point of view, literally. Instead of trying to draw some complicated curvy line in 2 dimensions, what if we could just lift the data into a 3rd dimension? All of a sudden, that jumbled mess could become perfectly separable with just a simple, flat plane. And that's the core idea here. Map the data into a higher dimensional space where everything becomes simpler.
And this new perspective? Well, it has a name. We call it the feature space. The mapping that gets us there, which we note as phi of x, takes our original data points and transforms them into these new feature vectors. The whole goal is that in this new higher dimensional space, all those complex relationships from before suddenly look simple and, you guessed it, linear.
Okay, that sounds awesome in theory, but wait a minute, aren't we talking about projecting every single data point into, like, a million-dimensional space or something? That sounds incredibly complex, and computationally, it sounds like a complete nightmare. Is that even practical?
You know what? It would be a nightmare, but this is where the magic really happens. It turns out that for a lot of algorithms, we don't actually need the new coordinates of the points themselves. All we need to know is the relationship, the dot product, between pairs of points in that new space. And we can get this result without ever actually going there, thanks to something called the kernel trick.
So a kernel function is basically a genius shortcut. It gives you the answer you need, that inner product from the super complex feature space, but it calculates it using a simple operation on your original easy-to-handle data. And what's so cool about this formula here is that we get the result of the dot product, phi of x, phi of z, without ever having to figure out what phi of x or phi of z are individually. It's just a brilliant piece of math.
So let's just break that down. The brute force way is this slow 2-step process. First, map everything to the high-dimensional space. Then, compute the inner product. But the kernel way, you just compute k of xz directly on the original data. One simple step to get the exact same result. That's what makes this whole idea practical.
All right, so the kernel trick is this amazing shortcut for dealing with messy nonlinear data. We get it, but how do we actually use it to find the best possible separating line in that new space? And that's where something called a support vector machine, or SVM, comes into play. See, an SVM isn't content with just any line that separates the classes. Nope, it's specifically designed to find the absolute best one possible. When you combine the kernel trick with an SVM, you get an incredibly powerful classifier for all sorts of problems. So how does it find the best one? It looks for what's called the maximal margin hyperplane. The idea here is actually really simple. Think of it like you're paving a road between 2 different neighborhoods of data points. You don't want a narrow little alley, right? You want the widest, safest road possible, with the biggest buffer zone on either side. That buffer is the margin, and making it as wide as possible makes our classifier way more robust. And right on the edge of that wide road, you'll find a few critical data points. These are the points that give the algorithm its name. They're the support vectors, because they are literally the points that support or define that boundary. In fact, you could move around all the other data points, and as long as they don't cross into that margin, the boundary line wouldn't budge one bit. It's all about these critical few.
Okay, so this all makes a ton of sense when we're talking about numerical data, right? Stuff you can plot on a graph, things you'd find in neat columns in a database. But what about all the other kinds of data out there, in the real world? Can we apply this same idea to things like text documents, or even the structure of molecules?
And this is where kernel methods go from being cool to being an absolute game changer. The answer is a huge yes. By designing the right kind of kernel function, you can apply this entire framework to all sorts of incredibly diverse data. We're talking strings for text analysis, trees for looking at sentence structures, and yep, even entire images.
And that's really the secret sauce here. The versatility is just incredible. As long as you can define a valid kernel function, which is really just a meaningful way to measure the similarity between 2 things, you can use an SVM. It's kind of like the algorithm has a plug-and-play slot. Need to work with text? Plug in the string kernel. Working with images? Plug in an image kernel. The core SVM algorithm doesn't even have to change.
So when you boil it all down, kernel methods teach us a really profound lesson about data analysis. Sometimes the most tangled, complex problems can become shockingly simple if you just find the right way to look at them. The right kernel is like putting on the right pair of glasses. It can bring fuzzy, overlapping patterns into sharp, separable focus. So what unseen patterns could be hiding in your data, just waiting for you to change your perspective?
Hey, if you enjoyed this explainer and it helped you see things from a new perspective, do us a huge favor and hit that like button, share it with someone, and subscribe for more deep dives. Thanks so much for watching.